Hi folks, let's talk magnetic fields and quote long wires. Here's a current carrier carrying current in the direction shown. First question, very valid question, is what's the field around near this wire look like? Well, that direction is defined by Biot-Savart, which is to say that there are field contributions that depend on size of current, some constant stuff, and a cross product. All right, so really what we care about, I mean, sometimes you'll see this written as IDL, maybe more commonly you'll see it written as, come on, as IDL cross R hat. Oh, and I forgot that part. Well, look, if current's going that way, what we can say is like, okay, here's a little what I call, or what can be referred to as a current element, IDL. And well, if we say like, how about here, at that location, here is an R hat unit vector that points in the direction of the R vector that locates our location of interest. And then what you do is, well, right-hand rule as it applies, I mean, dB vector equals constant stuff times this cross product. So we go right-hand fingers, and we curl our fingers towards that direction, and right thumb will point in direction of the answer. So our right fingers go this way, I curl my fingers that way, and my thumb at this location points into the screen. Yeah? Well, guess what? At a place up here, the only difference would be the direction that I curl my fingers toward. Stop that. So here we go. What are you doing? Just stop that. So I would curl my fingers this way, and my thumb will end up pointing out of the page, and we get a field that looks like that. Okay, well, in the plane of the page, that's the only stuff I can draw. So what might be of some value is to, hey, don't look too far ahead. What might be of some value is to say, let's take the current from a different perspective. Let's say that this current is now, how about coming at us? How about instead of that, because it's going to make it might make your right hand rules physically painful. Let's say the current's going away from you. You're welcome. That means we can always point our fingers into the page, our right fingers into the page. And if we were to say curl them towards that location, the field would point upward. I'm gonna make the field point out of the page because don't worry about why. So okay, so fingers out of the page, I curl them toward this location, and my thumb points down. Here's a magnetic field there. Guess what? Over here, magnetic field points up. Guess what? Here, magnetic field, oh please, magnetic field up here, fingers out of the page, curl them, ouch, upward, and we get a B that way. And guess what? We get a B this way. And so at any place, the direction of IDL and R hat are perpendicular, and so you're always going to get a B that points perpendicular to those other two vectors. And what you get is a field that does this. Magnetic fields are continuous. It's a circle. All right. So if we what this actually shows us is that there's a field that looks something like this. Ooh, wait, hang on. Looks something like that. You get me now. I'm just trying to use some fancy graphics to show that the field goes behind the wire like that, right? You get me. Right? Okay? Yeah? So fields wrap around current carriers. Sure. And I'm not, I hope you understand, I'm not saying that the field stops and starts. The field is continuous. I'm trying to give some sort of three-dimensional perspective. Yeah? And I could certainly make this one better. Watch. The field really does this. Boink. Yeah. And this one happens to, come here. Come on. There you go. Sure. And this field, yes, goes this way, this way, this way, this way, this way, and so on and so on. Well, guess what? There's another right-hand rule that you can use to identify the direction of a magnetic field near a current carrier, right? One is Biot-Savart and the inherent truth of all cross products, how you evaluate the direction of a cross product. Well, we can use a quote-unquote trick that says what we can do is point your right thumb in direction of current. And when we mean current, we mean conventional current. Conventional current defined to be the direction of hypothetical free positive charge flow. You do that, and your right thumb, your thumb in the direction of current, sure. Your right fingers curl in the direction of the magnetic field. That's a right-hand rule for current carriers. Yeah. So here, look, we point our right thumb out of the page, and our fingers, when we curl them up, wrap around that way. Right? Sure. And here we put our right thumb pointing that way. Boy, right-hand rules are the worst thing to teach via video. That's fine. We point our right thumb this way, and when we curl our fingers, we can imagine our fingers curling up behind the wire and over the top coming out of the page and down in the front of the wire and so on and so forth. Okay? Yes? Great, onward. Here are two current carriers, and these things each carry the same current in different directions, and there are a couple of locations that I've located such that you can see. And the question is, what's the field at each of those two locations? Well, one thing we need to know is, okay, here's the direction. So we find the direction of a field with some right-hand rule stuff. We in my class, we've used this to really crank through a whole bunch of substitution and trigonometry and calculus and blah, blah, blah to show or to generate the idea or the physical truth that the field, the magnitude at least of a field near a long current carrier goes like this. mu naught I over 2 pi r, where r is distance away from wire. That's magnitude of field. And then the above stuff is how we find direction of field. Yeah. So let's look at cases like this where there are multiple current carriers. So at this location in the middle, what we can say is, all right, what's strength and direction of total field? Well, there are two contributions to the field. There's the red field at this location. Okay, right thumb downward, right? And then fingers wrap, wish you could see my hand. Fingers wrap around this wire. My right fingers, everywhere in here, point this way, out of the page. Yeah? Okay, yes, you get it. And okay, now let's put our right thumb upward to find the field made by this current carrier. And in between these wires, well, guess what? My right fingers also point out of the page. So in there, the field contributions from each current carrier point in the same direction. So here, I would say that how about this? The net magnetic field is, let's see, that one plus that one, because they point in the same direction. Okay, and each of these, we've done you the service of, well, we can say that these are each mu naught I over, in this case, 2 pi d, plus, I think you follow, mu naught I over another 2 pi d. And okay, that happens to be the net B in the, peek, the net magnetic field in between the, oh boy, is mu naught I over pi d outward vector. Yeah? Fine? Good? Great. What about up hither, up yonder, this location? Well, let's see. Everywhere to the right of this pink wire, my fingers will point out of the page. The field gets weaker the farther we get away from this pink wire, but it does always point out of the page. But now if I put my right thumb pointing towards the top of the page, my fingers would bang into the screen here. So the blue field contribution points inward, and thus here our net field expression, notice that we apparently have defined outward to be positive. So it looks like we say this and minus that. Different directions of these fields. All right, so, all right, now this B is mu naught I over 2 pi r. Well, how far from this wire is this point? 3D minus mu naught I over 2 pi d. So our net field is a sixth minus a half. That's a sixth minus 3/6, right? Yeah, sixth minus 3/6 is negative 2/6, negative 1/3, negative. Or how about this? Mu naught I over 3 pi d inward. Pretty sure my algebra is right. You dig? Notice we get a net negative field, but because we have, at least here, defined positive to be outward, when we get a negative answer, well, I don't put negative in the, I'm not going to say negative, I'm going to interpret the significance of that negative. Yeah? And yeah, sure, of course. Like, which field is, this field is stronger than that one by a factor of 3. The field in between is stronger than the field out here for one of a couple of reasons. One, all these fields point in the same direction. Two, you're, well, quote, close to each of these things. Out here we have fields that point in separate directions, and you're farther away from one of those current carriers than you were the other. So a couple of reasons that sure seem to make sense. 6 minus a half. 6 minus 3/6. Yep, just check. Negative 2/6. Yeah, okay, good. Onward. Great. Here's a different one. Oh, how about this? This is supposed to be like, in green. It's supposed to be, this is supposed to be like a box, a square, I guess I would call that, of all the same. Let's call it, like, these are all A's. Let's call them these all A's. This is all A, and all the rest are all A's. But now I've got two different currents. All right. I'll do a couple of them. How about we do this one here? Yeah, shan't we? So let's look at contributions from each current carrier. Well, from the blue, right thumb upward, fingers point out of the page. From the green, right thumb to the left, fingers would tap into the page. So up here, my net B would be, how about this? The one pointing outward is stronger because it's a stronger current. So I'm going to say, I'm just going to write it like this: B from the 3I minus B from the 1I. There. So that net B, all right, mu naught, oh wait, mu naught 3I over 2A minus mu naught I over 2A. So our net B, I messed up I, didn't I? 2 pi A, 2 pi A. So that happens to be 2 mu naught I over 2 pi A. So how about mu naught I over pi A out? Yeah? Why the box on there? How about down here? While we're at it, let's see. From the blue, still like this. From the green, right them. Oh, also out. Maybe not a big surprise there. If above the green wire we're in, and then below the green wire, why would we not be outward? And so net B down here, net B down here is, well, we can add these. B3 plus B1. Well, here's the strength of each, but now we simply add them. So 3 mu naught I over 2 pi A plus mu naught I over 2 pi A. We get positive 4 over 2 mu naught I over pi A also out. Yeah, fair. And you can do the other two spots if you want. I'll spare you. For some of you out there, we're taking maybe a leap of faith with this. That's okay. A follow-on video will show you. Well, here's the hard way. Hang on, wait. Here's the hard way of getting there. I'll show you the quote-unquote easy way in the next video. All right, but the idea is we want to be able to combine what we know about directions of fields, and we have a couple different ways to figure out those directions. I would really try to work on that way where IU. And using that and an expression for strength of fields, we can find net field strength at any location or at some locations. Okay, thank you.